dimension and how it leads to different crystalline structure. And so you can have a symmetry which can be cubic or hexagonal, and that is and on the crystals or the atoms, they follow a translation symmetry, and they are arranged in a geometry which can be represented by a unit cell. And when you repeat that unit cell over the 3 dimensions, so you can obtain the crystal. And normally that crystal mathematically you represent by arrangement of points, which we call lattice. And then if you attach atoms or molecules, or maybe more than one atom, to one lattice point, so you create the crystal. So it is basically lattice plus these atoms or molecules, which we call as basis, so they will construct the crystal. But that is like one of the ideal scenario, right? So where you have all the atoms occupying all the positions. But in many cases, and actually what happens in reality is that you have defects in crystals. So here is one example. So if you look at the left most picture, the figure A, so it represents a perfect crystal. So all the atoms are occupying all the regular positions. But it can happen that, so normally these atoms are actually not static. So they always vibrate because you are mostly, the temperature is more than 0 Kelvin. So they will always have a thermal vibration, and these atoms, they vibrate around their mean position, and this is due to the thermal or the temperature. And it might happen that for some atom, it's like a statistical thing. So it can happen that one atom, the thermal energy, so this thermal energy is like a average energy which is experienced by the atom, but maybe one atom has a higher energy, gets higher energy, and it gets displaced from its regular position, like shown in the figure B here. So if you look at this figure here, so what is happening is, so one atom on the surface here, the dotted one, so it is displaced from its original position and probably will sit on the surface attached to another atom. And this is due to it gets an extra energy due to the thermal vibration, or maybe interacting with neighboring atoms and so on. And that is what, now you have a defect in this crystal. Okay, so now it can also, it is also happen, this defect, so they can actually move in the crystal as well. And how they will move? Now, since there is a vacancy here, so this defect, we are calling it it's a vacancy, because it's a vacant atom. There is no atom, so it is the place is vacant, so it is known as vacancy. So now this vacancy can be occupied by a neighboring atom, so which is like one neighboring atom from the below will jump. So it is jumping from here to here, and the vacancy basically moves downwards. So it can happen that this vacancy actually can move, like see in the figure C and figure D, what you see is the atom is occupying the vacancy or vacant position, and the vacancy is actually moving through the crystal. So it may happen, this vacancy, it need not to move only in the direction like shown here, so it can move in the either left, right, or down. So basically what happens is, this atom, we call the atom diffuses into the crystal. So the term is there is a diffusion of the vacancy into the crystal. So most likely the vacancy will start or will occur on the surface, but eventually it can happen that vacancy will move inwards into the bulk of the material or diffuse into the bulk of the material. So these are actually basically a thermodynamic effect, or sometimes it's also known as a thermodynamic defect as well. So the key thing here is this diffusion of vacancy, which is created due to this random thermal vibration of atoms. These vacancies, they can move inside the material, or you can say it is diffusion of vacancy inside the material. So this is, but again, it is a qualitative way of looking at this creation of vacancies or defect. But there is a thermodynamic, this thermodynamic effect can be described by an equation where we can say how many vacancies are created at a particular temperature. So if you are, if the material is at certain temperature T, so let's say T is the temperature. So since it is a thermal effect, so or a thermal vibration, so the system, the average energy will be like kBT. Okay, so this is your average energy. So some atoms can have a little bit higher than this energy, some atoms can have lower, less than this energy, but the average energy will be of this at equilibrium will be kB into T. And this will create a equilibrium distribution of vacancies. So it is not like all the atomic positions will be will become irregular or displaced. All the atoms will be displaced from their position. So, but some of the atoms will be displaced from their regular position. And this number NV, so which we represent, so here we call it NV, or number of vacancy per unit volume. Which you can write it down as. Sorry, can you mute?
मुझे पता है आपकी कोई बात.
हाँ, चल करो.
Excuse me, hello? You should mute. Everyone should mute your mic. Kshitij? Yeah, you should mute your mic. Okay, thank you. So this number of vacancy per unit volume will be equal to exponential. So it will be proportional to this term exponential minus EV by KBT, and it will be multiplied by N, which is this capital N, and capital N is actually number of atoms per unit volume. And what is EV? So EV is nothing but activation energy, the energy required to create that vacancy. So you need certain energy, this EV, which will be most likely greater than the bonding energy, so that because when the atom is getting displaced, you need to break the bond. So this would be higher than the bonding energy. So once this atom gets that much activation energy, so it will be displaced from its position. And you can calculate the number of vacancies, and at like the equilibrium distribution of these numbers at a particular temperature T, if you know what is the activation energy. And you can also see that this number of vacancy or the defects will actually increase as you increase the temperature. And the reason being, more and more atoms, the activation energy, and this, where do they get this activation energy from? So basically from the thermal energy, that is from where they will get the activation energy. And as you increase the temperature, so the thermal energy will be higher, and therefore the probability of breaking these bonds will be much higher, and therefore you will have more number of vacancies as you increase the temperature. And so here is actually a picture of this how these different vacancies actually in the crystal play a role in terms of the how they modify the structure. So when you create these vacancies, as I said, so they will move in the or diffuse into the material, and they will create a environment which is different from the regular arrangement of atoms. So normally these vacancies are known as point defects. So vacancy is known as a point defect. So there can be other form of defect as well in a crystal, but normally these so since vacancy just like a point, so it's like, therefore it's known as a point defect. But there can be other point defects as well. So one is this vacancy that you have created here, like let's see here in this figure. So it is a point defect, which is vacancy. You can also have another kind of defect. So one is this vacancy. Then you have a substitutional defect. Okay. So what is a substitutional defect? So if you look at the figure B and C here, so what you have is another atom. So let's say you have a vacancy for some reason, but another atom, a bigger or a smaller atom, can go and sit in that vacancy as well. So it is like a impurity. So you have a impurity here. This is an impurity atom. So it can be large or it can be small. So they can go and occupy that vacant position. And that is is known as a substitutional impurity, and it's like a substitutional defect. Okay, so you can replace that vacancy by another kind of atom. Okay, so not the atom which makes the crystal, and therefore they are called as impurity atom. And then, so this impurity atom, this substitution normally happens in like when we say, so these are possible statistically, or you may not be wanted, but in semiconductors, when we say doping, we deliberately put these, make this substitution. Okay, so when we want to make a p-type or n-type semiconductor, so if you have silicon, which is intrinsic, but if you want to make it a p-type or n-type, so you want to substitute, so like you want to put boron, or maybe phosphorus or arsenic, okay, so that you make it p-type or n-type. And to do that, so you have to deliberately put these impurity atoms into silicon crystal. So sometimes it is not desired. In many alloys, for example, you don't want to have defects, but in semiconductors you really want this defect, but you want to put it in a controlled way. So then these are the second type, and the third type is interstitial defect. So these are all point defect. And what is interstitial? So if you look at this figure D here, so now within the lattice, what you have is some voids, okay, or some space that is still available for smaller atoms or ions to go and sit. And these interstitial positions, these atoms go and they can sit there, and this is known as a interstitial impurity. And so the example will be, so for the substitutional defect, the example will be, so let's take a couple of examples. So if you put, so let's take a silicon crystal, and then you have a boron, or let's say arsenic. So those are the substitutional defect. And what is the interstitial defect? So one example is like you take an iron crystal and you can put carbon. They go to the interstitial sites. So that is so carbon atom is much smaller compared to the iron crystal, so they can go and sit somewhere. So this can be a example of a carbon atom, and if this is a iron crystal. Okay. So if you have a yes.
Sir, as you said that there are it is not it is unexpected in some semiconductors, and it is done in a controlled way.
Yes.
Doping is done in a controlled way. And what exactly is the controlled way of doping?
Controlled way, we may not discuss that. The controlled way means like you implant, so these defect or these impurity atoms. So what you want is these atoms should go and sit at certain position, and then you want there should be a number of these impurity atoms should be fixed, or should be, you should decide what should be the how many impurity atoms you want to put, because what ultimately these impurity atoms decide is the number of charge carriers. So let's say if you have a n-type, so you have electrons, so you can increase the number of electrons by changing this number of impurity atoms. So if you are doping it with, let's say, arsenic or phosphorus, so if you have an extra electron, so you get like n-type, and then you can increase this number of electrons n by changing this number of impurity atoms. And so in semiconductors, so you want, whether you would like to have, and we will see later on today, so how n, this number will actually is related to the conductivity sigma. Okay, so if you change the number n, so you change the conductivity of the material, and therefore you want to have so for devices, so you want to have certain conductivity, and therefore you want to control what should be the value of n. And how you will control that n? So by controlled doping. Okay, so that is what I mean by controlled doping, and that you do normally. There are several ways. So you can and typically it's done by something known as a ion implantation. Okay, so you can actually implant ions. So in this case, let's say arsenic or phosphorus, for example. So you can implant in an intrinsic semiconductor, and how do you control that? So you need to control the concentration of these ions that you are trying to implant. You want to control the energy of these ions. Okay, so and also you have to maintain a particular temperature. Okay, so when you are doing this ion implantation, because these are high energetic ions, so they can also increase the energy of the crystal itself. So when they are going inside and they can sit somewhere, but they have to, so they have certain kinetic energy, but then they will release that kinetic energy, and that can actually increase the temperature of the material as well. So you have to also maintain the temperature. So so these are the parameters which you need to control, and that is what I mean by controlled implantation, controlled doping.
Okay, sir. And
Yes.
how is the graph related? Like if we increase the number of n, then how the sigma changes?
Yes.
Like it is perfectly increasing or it is decreasing after a certain time?
Oh, it will increase. So for semiconductor, uh, so it will always increase. I mean, as long as you are putting more phosphorus or more dopant, so it will always keep on increasing, and it will happen that you can even make a silicon almost like a conductor. You can do that by doping actually. So if you have a very large amount of doping, so you can actually make the silicon even conducting as well. So silicon is semiconductor, but you can make it conducting by heavy doping. That is possible. But then you may not, I mean, you don't want to replace all silicon by some impurity atoms. So otherwise, that will become, again, what will happen is if you put more number of dopants, so they can form, and now, let's say if I put more number of boron, let's say. So now boron atoms will come and interact with each other. So they might form a crystal which is similar to boron. It may not represent silicon anymore. Okay, so you also don't want to dope too much as well, so that you retain the properties of silicon as well. Okay.
Okay, sir.
Okay. So as I said, so these are the different kind of doping that or substitutional defect or interstitial defects or point defects that you can have in a crystal. So we will come back when we discuss a little bit about semiconductor, intrinsic and extrinsic semiconductor. So we will discuss about this. Okay. So one thing which I could not discuss in the last class was the difference between a single crystal and polycrystal and what is grain. So here is a picture of a single crystal on the left hand side. So this is a single crystal, and this is a polycrystal. So this is a representation of these two different kinds of crystals. So sometimes, clearly in single crystal, what you see is throughout the material, both have long range periodicity. So long range periodicity is present in both single crystal and polycrystal. But what you see here is a single crystal. Throughout the material, the arrangement of atoms or the lattice is always regular. Wherever you go, it looks exactly the same. But in a polycrystal, what is happening is, so you have regions where you have long range order, but so the periodicity remains the same. You see, so the lattice parameter. So if I say this This is my lattice parameter. Okay, so this is my lattice parameter. So it is not changing. So the distance between two neighboring atoms is not changing. It is not changing in a single crystal as well as in the polycrystal case. What is changing is the orientation of this atom, how they are arranged. So this orientation, normally we represent it by, or we call it the lattice planes. Okay, so what you have is a change in orientation. Okay, so this orientation is changing. So somewhere the atoms are like that means, or we call this as a lattice planes. So these planes have different orientation when you go into different regions, and these different regions are known as grains. Okay, so these are known as grains. Okay, so this is one grain, this is another grain with a different orientation, this is another grain with different orientation, or orientation here means the lattice planes are different. Okay, so however the lattice parameter is not different. Lattice parameter in all the cases will remain the same. So these small regions which will basically uh, are again, they have a regular arrangement of atoms, but not like a single crystal where it extends throughout the material. So typically the size of these grains, so the grain size would be in the range of, so grain size would be in the range of few micrometer, and it can go up to maybe a few hundred micron. Okay, so few hundred micrometer. So in that range, grains are fragments. Fragments. I mean, they are. You can say they are a smaller version of a single crystal. So when you look at within each grain, so if you look at one grain, so it looks like a single. Yeah, you can call it a domain, but then yeah, similar to magnetic domains, what you can correlate with that. Yes. So when you look at,
Sir,
yes.
sir, can a polycrystal have multiple single crystal in exact same orientation?
No, 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 no. So that is not possible. No. So a polycrystal will be again. So if I have now here, you see, I have two kind of atoms which makes the crystal. So it's a blue and the red atoms. So you have the same blue and red atoms actually, or maybe it can be one particular atom, but you cannot have different lattice parameter. So what you are saying is you have a different lattice parameter, and then the orientation is different. So in that case, you don't call it a polycrystal, rather it will be an alloy, or maybe a mixture up to different
No, sir,
materials.
lattice parameter is not different. I'm taking a single crystal and it is all the multiple crystals are having same lattice parameter, and I'm keeping it in the same orientation.
Yeah, then in that case, it will look like the picture here, no? So if you are keeping the lattice parameter same, and you are saying it is the orientation, you are also keeping the same, right?
Sir, but there will be no bond between them, no? The two multiple single crystals.
So let me see. So your question is,
Mm,
let's see. Just put it here. So what you are saying is, if I understand, so you are saying, so you have different regions, okay? And what you have is, let's say this is like one thing, and how will be the orientation here in the second, in this part lecture?
Same orientation.
The same orientation.
Yes.
But then why there will be a boundary then? The boundary will not exist in that case because it is a continuous, the same repetition and same atoms are there.
Okay, sir. Got it.
Okay. So your, like if you think about this bulk material, so this may not happen, but when people go to thin films, so your case will be very interesting when you go to make thin films. Okay. So when you make thin films, for example, so you have a silicon crystal. So what we are doing is looking at a cross section. Okay. So I want to grow or coat another material on top of it. Okay, so very thin film. So typically, let's say I would say maybe 1 micron thick. Okay, or maybe sometimes you can go even lower thickness. So it can be like 100 nanometer or even less than that. Okay, so you want to grow a thin film on a silicon layer. Okay, when you grow this thin layer, so what happens is typically this is a different material. So very good example is actually you can grow the silicon dioxide, thin silicon dioxide on silicon, and what you do is, and the silicon dioxide, silicon will have different lattice parameters. Okay, but since they are really so thin, so normally the silicon lattice parameter, so in this case, let's say the lattice parameter of silicon dioxide will be equal to lattice, sorry, so lattice parameter of silicon. Although in a bulk form, they are not same, but in this thin film structure, so it is possible that this lattice parameter can be same. And this is this typically happens in thin film growth. So it is a thin film growth of, let's say, SiO2 on silicon. So in this case, silicon oxide, it is not an amorphous one what we are talking about. So you can think silicon dioxide is amorphous, but here what we are talking about a crystalline silicon dioxide. So silicon dioxide can exist in a crystalline form as well. So it is a crystalline form. And since it is thin, so it basically repeats or just sits in on top of the silicon atoms. Okay, and although it is a different material, so it is we can call it a heterostructure. So the names are actually, again, from the name you can understand what is a heterostructure. So hetero means different. So they are different structure, but they have the same lattice parameter. So lattice parameter is so you can actually grow this single crystal structure, and it will be exactly like a single crystal. It will look like when you look at the atomic, like you zoom in, use a very good microscope, which is normally an electron microscope, and you use that. So if you look at carefully at the atomic arrangement, they will be exactly like this. And typically, it happens for very thin films. Okay, although again, now you have a different material, silicon dioxide and silicon. So it can also happen, for example, many heterostructures in semiconductor, it happens quite often. So if we have time, maybe we will also discuss about that. Okay. Yeah, we will touch upon that point in maybe next week. Okay. So here is this again coming back to this crystalline and polycrystalline material. So why do you have this polycrystalline material they form? So it is because of this solidification process. So when we talk about a solidification, so what you having, you So just look at the figure A here. So what you have is mostly a molten metal or a liquid, and now you are cooling down it slowly. So what happens? So some of the atoms will form a regular arrangement, which we call as a process nucleation. So these are known as nuclei, or so this is one called as a nucleus, let's say. And so there are many such nuclei, they will form or they will nucleate. So the term is nucleate. So they will nucleate many of these small crystallites or nuclei. And these nuclei will actually grow as you again further lower the temperature. So the nuclei will grow and they will form the crystal. But what happens, you do the solidification, what is happening is you don't have only one single nuclei or nucleus, you have many nuclei, and these nuclei have different orientation. Okay, and since this is a more like a random process, so it may not happen the tiniest crystal that form here has orientation like this, but the other crystal, so it might have a orientation which is different from this one. And now these nuclei or this nucleus will grow, as you see here in the second picture, B. So they are growing, and then ultimately when you are way below the melting temperature, so you have the solidification will be complete, and then you have this polycrystalline form. So you have grain, and then the boundary. What is the boundary? Boundary is known as a grain boundary. Okay, so which will differentiate between two grains. So this is why this polycrystalline, typically when you do a solidification, you will get polycrystalline material. And therefore, in material science or in industry, so it is, silicon, when it is used in a single crystal form. So therefore, this growth of silicon single crystal is really, it's not that easy, okay? And there are techniques which are used to grow single crystal of silicon, which they can grow like what you call is a wafer. Okay, so they wafer single crystal silicon in the form of wafer, which has dimension of like maybe 200 millimeter. So nuclei is nothing but you can say it's a single crystal, but there are not many atoms actually in a nucleus. So maybe like 10 atoms or 20 atoms, so they will form a regular structure. Okay, so it is not like in the single crystal. So the number of atoms can be like millions. Okay, so if you talk about 1 millimeter of a single crystal, but the nuclei will be very small. So maybe 20 atoms or 50 atoms, 100 atoms, that kind of number you have. And that number will grow as you start to cool down. Okay, as the temperature you reduce. So you are at the melting temperature. So that means it is in the molten state or a liquid state. Now you cool down. So as you go further below the melting temperature, so more and more atoms will then join this nuclei. So it will grow. So nucleation, that is growth, and then the solidification. So you can grow like 200 millimeter or even 300 millimeter diameter wafers, which are actually pure single crystal, which is very challenging. And you cannot, and that's why actually one of the reasons why silicon is so famous. So in case of, so one of the reasons, so not the only reason. So in case of other semiconductor material, it is very difficult to grow a single crystal of this large size, this wafer size. So that's why silicon is one of the, that is the only one which is used for chip manufacturing, because you can grow this single crystal, large single crystals. And then when you look at the grain boundary, so what you have is very interesting things happen at the grain boundary. Okay, so grains are okay, of course, regular arrangement you have somehow a crystal. But grain boundary is very interesting because so you can have many things that can happen at the grain boundary. So here, these are the few things which we have pointed out. So you can have an impurity. Many impurity atoms can go and sit in the grain boundary. You can have vacancies or defects, and then you can have dangling bonds or broken bonds, or so many things can happen. So this is a region which is, this is the grain boundary, so which is normally atoms have higher energy here. So atoms with higher energy normally will go to this grain boundary. Okay, so this is again another field in the material science. So, but we will not look at this grain boundaries in this course, but it is also interesting. And what is a grain boundary? Grain boundary is nothing but where two grains meet. Okay, so that is the grain boundary. Okay, so since we have some time, so we will, so if you have any other question. Okay, so if not, so we will start. So far, what we did is we looked at the arrangement of atoms and we looked at their structure. Okay, so now we will look at one of the properties of the material. So let's say we call this is the electrical properties. Okay, and then we see how we can differentiate the materials based on this electric properties. So when we talk about electric properties, so that means what we mean by that is this conduction of electrons in the material. Conduction of electrons, or it can be other charge carriers. So it is a charge carrier. Now, how do you move a charge carrier? For that, you need to apply a electric field. So you need an electric field, and you study how the charge carrier or electron, let's say, will move in presence of an electric field. So that electric field normally you represent by a voltage. And when you apply a voltage, and due to this movement or conduction of the charge carriers, what you get is a electric current. So which is related by the Ohm's law, which you all know. So which will be V is equal to I into R. So your V is the voltage, I is the current, and what is R? That is the resistance. And how do you define the resistance of a material? So normally you write resistance in ohm. And resistance is nothing but, it depends on the dimension of the material. So it depends on the dimension. So the length and the cross-sectional area. So rho is the resistivity, which is a dimensionless, or not dimensionless, but doesn't depend on the material dimension. Okay, so what is, so it is a, so then you can compare different materials having different resistivity, because it doesn't depend on the dimension of the material. And the unit is normally, it will be ohm, either centimeter or ohm meter. Okay, so this is the resistivity. Then what is the reciprocal of resistivity? That is your conductivity. which is your reciprocal of your resistivity. So that you will represent by O inverse, centimeter inverse, or ohm inverse, meter inverse. Okay, so this is the unit you can represent. So now let's look at certain resistivity values of material. So if I take, let's say, copper, so let's take copper. So resistivity of copper is 1.68 into 10 to the power minus 8. So we are writing all the unit here in ohm meter. Okay, so this is the unit. So if you take silver, silver has a resistivity, it's lower than copper, so better conductivity. Silver is a better conductor. So these are known as your conductors, okay, or metals. Most of the metals are good conductors. Then you have another class of material. So let's say look at silicon. Okay, so here the conductivity or the resistivity can vary. So something from 10 to the power 2 to of the order of 10 to the power minus 4. So all in ohm meter. So if you take similarly germanium, for example, so it can vary from 5 into 10 to the power minus 1 to 10 to the power minus 4. So you have similarly a gallium arsenide, another semiconductor. It's a compound semiconductor, 10 to the power 5 to 10 to the power minus 3. And these are the known as your semiconductor. So the resistivity is much higher compared to your metals. And you have a wide range in which the conductivity or the resistivity can vary. Why this variation? It becomes because of the doping. So what is the doping number of dopants in the semiconductor? So you can vary the resistivity or the conductivity. And the third type is the insulator, where example are, let's say, glass. So 1 into 10 to the power 11. So then another is like a diamond. Diamond is like really famous, of the order of 10 to the power 15 ohm meter. Okay, so the unit is always ohm into meter. So these are like insulators where the resistivity is really, really high. So then how do we, so this is like the absolute measurement, but how do we distinguish between them? So one needs to perform a temperature dependent resistivity study. So if you plot temperature or resistivity as a function of temperature, so you can then distinguish between these materials. So let's say if I take a metal, so I'm plotting rho as a function of T. So metal will be something like this. Okay, so I'm plotting it for the entire temperature range. So if you go to a low temperature, so this is what the resistivity you will get. So we'll discuss a little more in detail tomorrow. So, and now if you take a semiconductor, so semiconductor will be, let's say, something like this. Okay, and then if you take, so I don't have a place here, but let me plot here. So this is an insulator. So insulator will be somewhere here. Okay, so much higher than the, so it is not up to the scale, but it will be much higher than the semiconductor. So this is your insulator, and this is your semiconductor, and this is your metal. So from the temperature dependence of the resistivity, you can find out which material, which one is which material. So maybe in the absolute term, it may be sometimes difficult, but the slopes are different when you measure the resistivity as a function of temperature for metal, semiconductor, and insulator. So we'll discuss a little more in the next class about this. Yeah, so there is one question I think I answered. Oh yeah, from one key. Solidification is used to only make polycrystals. No. So solidification. So if you take a regular, so in the process of solidification, so you can make polycrystal. You can also make single crystal. You can make amorphous as well. That is also possible. So if I solidify rapidly, so if I cool down rapidly, so which is known as a process known as quenching. Okay, so if I do a quenching, so then that means I am at a higher temperature in the molten state and I rapidly cool it down. So that is known as quenching. So if I do that, in that case, I will get an amorphous material, because what is happening is there is not enough time for atoms to arrange in a regular order, because atoms need to move and find their equilibrium position. So if you don't give enough time, then they will it will be like an amorphous system. Now in a polycrystal, so typically if you cool down in a certain rate, so not that fast, so you'll always get a polycrystal. But if you really cool down very slowly, so in that case you give enough time for the atoms to move around and find the equilibrium position, and in that case you can find a single crystal. Okay, so it is not like only solidification will give to polycrystal. So you can get both all single crystal, polycrystal, or a amorphous material as well. Okay, any other question? Okay, so if not, so then thank you. So we'll then meet in the next class and then discuss more about this conductivity, electrical conductivity in materials. Thank you.